Imagine yourself suspended at the very brink of a colossal black hole, where space and time warp in ways that defy belief. As you glance back, you see not merely endless darkness but hundreds of versions of your own form repeating in an eerie procession, much like phantoms echoing through an infinite corridor of mirrors. This is no sorcery or hallucinatory dream, it is the photon sphere phenomenon. Light becomes ensnared in a flawless orbit, bending your vision so profoundly that you can behold your own back from every conceivable angle. In a mere 15 seconds, even the final strand of light succumbs, unable to escape, and you are drawn into a realm where everything transforms irrevocably. Today, we embark on an exploration of a subject that quickens the pulse and provokes profound introspection: what truly transpires when a black hole engulfs you. This is no fanciful narrative from Hollywood cinema but a reasoned deduction grounded in decades of astronomical observations and meticulous calculations, validated by the unyielding principles of physics. Before commencing this dramatic odyssey, let us pause to clarify the essence of a black hole, for this forms the bedrock upon which all else rests. The eminent physicist Albert Einstein, who revolutionized our perception of the cosmos, once likened black holes to the divine attempting division by zero, an absurdity so profound that he believed they could not exist in reality. Einstein envisioned the universe as harmonious, devoid of such bizarre anomalies, yet humanity has proven certain of his misjudgments correct. When immense stars, far exceeding the mass of our Sun, reach the terminus of their existence at densities beyond imagination, they do not merely fade gently, instead, they undergo a tempestuous cosmic metamorphosis. The star collapses inward, compressing all its matter into a singular point. This begets the singularity, an enigmatic locus within spacetime where density is deemed infinite, and thus gravity attains infinity as well. One might envisage this as a rubber ball crushed utterly beyond recognition, but on a cosmic scale, where space itself bends in obedience to this formidable force. Einstein's general theory of relativity, unveiled in 1915, presented revolutionary concepts that continue to astonish scientists to this day. It posits that gravity is not a direct pull akin to magnetism but the consequence of spacetime curvature induced by mass. Picture spacetime as a taut sheet of fabric. A heavy object, such as the Sun, depresses it into a dimple, and lighter bodies, like Earth, roll along the resultant curve. This elegantly elucidates why Earth orbits the Sun and why planets dance in harmonious patterns around their stellar abodes in the solar system. The theory also foretold phenomena like gravitational waves, ripples in spacetime detected in 2015 by the Laser Interferometer Gravitational Wave Observatory from colliding neutron stars. Within a black hole, there exists no mere dark surface as popularly imagined. The singularity is so compact that it distorts spacetime to extremes, forging a deep well with walls nearly perpendicular. Anything plummeting into this abyss is inexorably drawn downward, with no avenue for escape. In 1939, Einstein published a scientific paper asserting that stellar collapse into a singularity was irrational and unlikely in the actual universe, fearing it might shatter the laws of physics. Yet, ironically, that same year, J. Robert Oppenheimer, later renowned for the atomic bomb project, and physicist Hartland Snyder authored a paper predicting that upon exhausting its fuel, a star's core succumbs to gravity beyond the neutron star limit, collapsing to form a region from which even light cannot flee. Employing general relativity, they essentially demonstrated what we now term black holes. This inaugurated a new epoch in astrophysics, and presently, we observe hundreds of black holes via gravitational waves and direct imaging. For instance, in 2022, the Event Horizon Telescope unveiled the inaugural image of our galaxy's supermassive black hole, Sagittarius A. As of 2025, the latest observations indicate that Sagittarius A exhibits stable orbits for surrounding stars, defying expectations of tidal disruption, rendering it less destructive than previously surmised. This transforms our galactic center into an ideal laboratory for study. Furthermore, research by NASA and international astronomers has detected hot winds emanating from the black hole, akin to cosmic gales expelling matter beyond its grasp. The James Webb Space Telescope has illuminated massive star-forming clouds near Sagittarius A, unveiling vibrant giant stars and luminous cosmic dust. The discovery of these hot winds portrays the black hole not as static but as a living ocean teeming with unforeseen motions. Artificial intelligence analyses have disclosed Sagittarius A's rapid rotation, underscoring its dynamic character. Such revelations evoke a sense of the universe as a vibrant expanse brimming with concealed currents, far from the serene void once imagined. Now, returning to our initial query, what befalls one cast into a black hole? One of the most peculiar attributes of black holes is that any entity, be it a colossal star, an azure planet, or a diminutive human, can become one if compressed to the Schwarzschild radius. The German physicist Karl Schwarzschild, in 1916, derived the first exact solution to Einstein's field equations, a discovery both simple and exquisitely beautiful, akin to a flawless mathematical portrait. The Schwarzschild radius denotes the distance at which gravity becomes so intense that light cannot escape, delineating the event horizon, the ultimate boundary segregating the external world from the black hole's interior. For our Sun, compressing its mass into a sphere of 3 kilometers radius would abruptly transmute it into a black hole, consigning all nearby to eternal obscurity. What of Earth? Reduced to a 9 mm radius sphere, it would resemble a minuscule marble fitting in one's palm. For a human to become a black hole entails catastrophe beyond conception, compression smaller than a proton, billions of times tinier than an atom. Yet, should this occur, you too would possess your own gravitational dominion, albeit fleetingly. So, which black hole shall we select to compress you for this most captivating adventure? Primordial black holes from the Big Bang era, diminutive in scale, might evaporate swiftly per Stephen Hawking's 1974 radiation theory, rendering them less intriguing. Hawking radiation arises from quantum pairs of particles near the event horizon. One particle falls inward while its counterpart escapes, causing the black hole to forfeit mass and evaporate. This transpires rapidly for small black holes but over billions of years for larger ones. Recent theories suggest Hawking radiation presupposes an incomplete event horizon, implying we may have misconstrued black holes for 60 years. Moreover, studies propose primordial black holes emitted intense Hawking radiation post-Big Bang, potentially reshaping cosmic structure. Alternatively, supermassive black holes at galactic cores boast event horizons vaster than solar systems and masses billions of times the Sun's, yet their gravity disperses broadly, diluting the falling experience. Let us opt for proximity, Sagittarius A at our galaxy's heart. In truth, you orbit it already, as the entire galaxy whirls furiously about this entity. Sagittarius A harbors approximately 4 million solar masses and is one of two black holes humanity has imaged directly, the first being M87 in 2019, followed by Sagittarius A in 2022. By 2025, fresh Event Horizon Telescope observations depict hot winds around Sagittarius A, evoking the universe's fervent breath. Surrounding stars' orbits prove more stable than anticipated, demonstrating that black holes are not invariably destructive but occasionally permit uncanny equilibrium. This stability renders the galactic center an exemplary site for investigation. Let us now set the stage for this journey, evoking the tension of boarding a vessel bound for uncharted realms. Envision us halting our spacecraft at a secure distance of 100 billion meters from Sagittarius A's event horizon, close enough to sense an insidious tug, yet not overwhelming. I propel you towards the black hole while remaining aboard to observe from afar. Herein lies the crux. Per general relativity, your temporal experience near the black hole diverges utterly from mine, as the entity warps spacetime so fiercely, akin to a river abruptly kinking. Christopher Nolan's 2014 film Interstellar, advised scientifically by Kip Thorne, who garnered a Nobel Prize in 2017 for gravitational wave detection, vividly depicts this, instilling in viewers a poignant sense of isolation and helplessness. We equip ourselves with specialized chronometers, not ordinary timepieces, but devices precisely gauging time dilation from your perspective and mine aboard the ship. Thus, we witness two parallel worlds gradually sundering. With chronometers synchronized, your descent into the black hole formally commences. Initially, it feels like serene free float in vacant space, but the pull intensifies, inducing a subtle vibration through your form. Almost immediately, you behold the black hole devouring matter at terrifying velocities, resembling a cosmic beast with jaws agape. The spectacle is majestic. Encircling the black hole, a rotating disk of matter, the accretion disk, heats to millions of kelvins via friction, radiating brilliantly. Simulating this on an ordinary computer might consume over a decade due to the equation's complexity. In reality, the disk gleams in blue or white hues, though scientific visualizations often render it orange for observational clarity, with frictional sounds imaginable as a low, resonant roar. Glancing at your chronometer after what seems 30 minutes to you, with the journey merely 0.1% complete to the event horizon, I aboard the ship am ahead by 11 seconds, a disparity not yet grave. Yet solitude begins to encroach, as if time itself stretches languidly about you. Drawing nearer to the black hole, space-time curves intensely, birthing bizarre visual distortions, as though plunged into a warped reality. Light from both flanks, even behind the black hole, bends to reach your eyes, resembling beams dancing amid a storm. Checking time anew, 2 hours elapsed for you, 1.4% of the journey done, I lead by 44 seconds. This gap unnerves, though not catastrophically so. Your heart races, blending exhilaration with trepidation. The dark central void expands more rapidly than expected, courtesy of gravitational lensing, where light grazing you converges on your retinas, making the universe appear to contract around you. Much later, consulting the chronometer shocks you, 12 hours gone from your viewpoint, yet aboard the ship, I perceive you absent for 15.5 hours. This rift evokes reflections on life and loved ones, as if time pilfers precious instants. Now exceedingly proximate to the black hole, everything turns profoundly strange, heightening tension akin to science fiction. Before attaining the singularity, you traverse a wondrous, fantastical zone where gravity and light harmonize perfectly. Frozen there, gazing about instills awe, as if witnessing the universe's miracles. You have entered the photon sphere, one of the cosmos's most peculiar locales, situated at 1.5 times the Schwarzschild radius from the singularity. Here, gravity balances impeccably, permitting photons, particles of light, to orbit eternally like perpetual satellites. It is not matter emitting or reflecting light but photons themselves trapped in orbit, forging a faint luminous ring. Should a beam of light tangent the black hole, it spirals indefinitely, the slightest deviation sends photons plunging inward or fleeing outward. Under these precise conditions, frozen in the photon sphere, you behold infinite repetitions of yourself from behind, multiple replicas of your nape staring into the void. It is genuinely you, as if standing beside yourself, requiring no technology but arising from spacetime's curvature. This sensation mingles eeriness with wonder, whispering that the universe ensures you are not alone but enveloped by your own essence. Recent research delves deeper into the photon sphere via comparisons of gray body factors and emission rates in Hawking radiation, unveiling complexities in infinite series theories of black holes. Studies from 2025 explore topological charges of photon spheres in asymptotically flat spacetimes, offering novel insights into their formation and stability, while investigations into multiple photon spheres around hairy Schwarzschild black holes reveal interferometric signatures that could distinguish exotic black hole types. Continuing the descent, you approach the event horizon intimately. Having surpassed the photon sphere, the black hole dominates your vista, darkness gradually enveloping you like a creeping shroud. Imaginary winds howl through space. Space-time twists so that the black hole's rear and sides manifest ahead, alongside regions visible in flat space-time, crafting a vivid stereoscopic tableau. From your perspective, 13 hours since departing the ship, with 24 minutes to the event horizon. Excitement peaks, awaiting the fateful instant. Yet aboard, I have observed your journey for nearly 20 hours. Your 18 minutes equate to my 40 hours, normal to you, but to me, time toys with destiny. In the final throes, 6 minutes remain to the event horizon. Eyes closed, deep breath for courage, you consult the chronometer, which appears malfunctioning, indicating I have watched you for infinite time. It is no fault of the device, peculiar physics prevails. From the ship, I see you approach the event horizon over decades, eventually redshifting as light's wavelength elongates, observable only via infrared telescopes. A melancholic sentiment arises as a companion fades. Even in eternal life, I would never witness you truly crossing the event horizon. Your concluding 6 minutes stretch eternally from my vantage. This sounds like science fiction, yet it derives directly from Einstein's equations, an absolute verity confirmed by contemporary simulations and gravitational wave detections, with recent ring-down black holes affirming predictions by Einstein and Hawking. Now within the event horizon, a grander question looms: what occurs inside a black hole? Curiously, the precise moment of crossing eludes detection, no explosion or jolt, but a seamless transition. You still perceive the external universe, distant stars twinkling, our ship a beacon of hope. Yet, like every light ray, you inexorably head towards the singularity, an infinite density point of no return, where our physical laws crumble and time halts. Escaping its gravity demands surpassing light speed, impossible per Einstein's special relativity. A common misconception holds that from without, extreme time dilation permits viewing the universe's entire future as a rapid film. However, this is untrue. Optical aberration, distortion of light directions due to motion, compresses the external universe into a slender luminous ring as you near the singularity, a faint fiery halo encircling darkness. Ultimately, sufficiently close to the singularity, your feet drag forward, elongating your body in spaghettification, a whimsical term scientists employ for tidal forces rending you into elongated strands. You merge with the black hole, wandering the cosmos eternally. Merely contemplating this chills the spine, blending dread with irrepressible curiosity. Black holes, these enigmatic celestial bodies, captivate humanity while evoking terror before the universe's might. Should humanity's technology advance a further 100 million years, might we explore near-galactic center black holes? Cosmic voyagers, fasten your safety belts and prepare for a bizarre traversal of the universe. Curiosity propels us beyond limits. Today, we venture to the environs of the supermassive black hole in the M87 galaxy, 55 million light-years from Earth, pausing at several exquisite exoplanets beyond our Milky Way. First, welcome aboard this ultra-swift interstellar vessel. Spacious as a luxury hotel, it affords repose during the protracted voyage, with gentle music resonating and stars glittering through panoramic vistas. Why circular in design? Not for aesthetics alone, but to generate artificial gravity via centrifugal force, ensuring crew feel grounded rather than adrift. Fresh air and soft illumination abound. The circle's hub houses propulsion and control systems, the ship's pulsating heart and mind, drawing energy from nuclear fusion reactions. Flanking the core, exploration and landing craft dock, departing with a soft hum when needed. For planetary descents, these diminutive vessels play pivotal roles, like flexible appendages of the mothership. Yet M87's black hole lies tens of millions of light-years distant, humbling us before the cosmos's vastness. To traverse swiftly, we must exploit space-time shortcuts, wormholes. A transient wormhole orbits Saturn, a clandestine tunnel the universe proffers. Its placer and formation remain mysteries, but it offers the sole conduit to another galaxy. Per Einstein's general relativity, wormholes might bridge distant regions, though unobserved as yet. Formation could involve negative energy or exotic matter, with stability and safety unverified. Nonetheless, exploring the unknown demands risking today. True adventure thrills. Prepare, entering the wormhole spans billions of light-years at millions-fold speed, a sensation of mild elongation then abrupt release. Ahead looms the faint silhouette of M87's black hole, its accretion disk aglow like an eternal fiery ring. By 2025, novel Event Horizon Telescope imagery depicts fluctuating magnetic fields around M87, with polarization reversing from one direction in 2017 to the opposite in 2021, evidencing the black hole environment's chaos and perpetual evolution. Scientists from Harvard and other institutions note this magnetic flip reveals evolving polarization patterns, elucidating potent jet formation. The James Webb Telescope captures M87's colossal jet in infrared, exposing the black hole's feeding habits. These shifts emphasize that black holes are not inert but possess intricate dynamism. Our inaugural halt is Miller's Planet, inspired by interstellar yet rooted in genuine science. From afar, it mirrors Earth astonishingly, a surface veiled in shallow oceans, sans lofty peaks or forests, with endless horizons stretching over watery expanses evoking peace yet isolation. Deceived not by appearances, time flows utterly differently from Earth. 1 hour here equates to 7 Earth years, as if inhabiting a sluggish realm. Why? Extreme proximity to the black hole amplifies relativistic effects. Gravity induces profound time dilation. M87's black hole, 6.5 billion solar masses, wields gravity beyond comprehension, bending space and time like an invisible titanic grasp. Time decelerates astonishingly, and Miller's planet endures tidal forces spawning 1,200-meter waves, roaring aquatic mountains thundering ceaselessly. Returning to Earth post-visit, friends and kin age years, mingling astonishment with regret. Recent theories posit primordial black holes could alter exoplanet orbits via flybys, or dark matter might spawn black holes within planets, precipitating calamity. Such prospects heighten perils of black hole proximate worlds. Next, we arrive at man's planet. At first glance, a vast icy mass, with glacial valleys shimmering under starlight like a fairy tale frozen domain. Yet beauty belies peril, skin-rending frigid gales and cracking ice resound. Temperatures plummet, the surface encased in thick icy ramparts. Atmosphere heavy with ammonia gas stifles breath. Innumerable lethal traps lurk, the abyssal fissures that ensnare eternally. Solitude and bone-chilling cold pervade. Yet exploration beckons, potentially harboring clues to primordial cosmic environs and extremophile life viability, per NASA's astrobiology theories. Novel research on dark matter black holes devouring planets from within amplifies these worlds' instability. Beyond these hostile spheres, we reach Edmund's planet at last, akin to discovering an oasis post-desert trek, instilling relief and hope. This planet orbits not the black hole directly but a vast azure star, whose stable habitable zone permits genial conditions. Soft light and warm air prevail. Expansive skies host fluffy white clouds, firm terrain boasts verdant meadows and serene locales, kindling hopes of a new abode. Should humanity seek habitable planets in this system, Edmunds emerges ideal. Large vessels cannot land directly, so smaller craft are proposed. Stepping upon it evokes unparalleled exhilaration after cosmic wilderness wandering, the gentle breeze, unfamiliar soil scent. Of course, access proves arduous, but standing with companions, viewing M87's black hole as a colossal shadowy presence in the firmament, overwhelms with cosmic scale. Successfully establishing a human outpost here would herald a historic breakthrough, inaugurating a new era. Recent studies on primordial black hole flybys perturbing orbits prompt contemplation of such planets' longevity. Naturally, this interstellar odyssey's ultimate destination is M87's black hole. Employing planetary gravitational slingshots, orbits accelerated by gravity, we attain its forefront. The accretion disk blazes like eternal flames, beautiful yet terrifying, scorching heat and blinding radiance. Caution, the black hole's formidable gravity could ensnare the ship, like a torrent engulfing all. Ahead lies the event horizon, a one-way threshold whence light cannot return. No egress heightens tension and fear. Having journeyed thus far, shall we peer within? A rare opportunity. White hole theory, black hole's antithesis, expelling matter, prompt some scientists to speculate interiors linked to alternate universes, though unproven. This time, I pilot a diminutive craft inward, transmitting data earthward. Courage mingles with apprehension. Remain aboard the mothership, awaiting tidings. Should I not return by dawn, convey to mother I shan't dine tonight, a jest to ease strain. Thus, confronting the black hole solo evokes inescapable dread, gazing into infinite abyss. Fortunately, you accompany via the craft, fostering camaraderie. As the vessel hurtles towards the boundary, gravity intensifies with proximity, an unseen colossal hand gripping tightly, drawing deepward amid faint vibrations. Ahead, endless ebon chasm, surroundings warp, time slows. Stars extinguish sequentially like flickering candles. What awaits within? Mere infinite gloom? As life seems concluding, a four-dimensional hypercube manifests, a bizarre edifice where time becomes a spatial dimension. Herein, life's every instant unfurls before you, akin to entering a temporal tunnel, familiar images stirring nostalgia. Why such within a black hole? Therein, time and space concepts cease normality, perhaps pure consciousness structures persist. Per quantum theory and black hole entropy inferences. The fourth spatial dimension, unobservable elsewhere, transcends time and space. Scientists like Carlo Rovelli conjecture interiors as entropy-maximizing sites, potentially resolving the information paradox. From this hypercube, limited interaction with the past ensues, displacing objects, say. Odd sounds heard prior prove messages from futures you dispatch backward. All beheld within becomes part of this extraordinary tapestry, deepening comprehension of cosmic origins, structure, and our place. Profound enlightenment and connectedness ensue. Recent wormhole research proposes elongated, bumpy caterpillar-like conduits linking entangled black holes, stable sans exotic matter, implying black holes as portals. Novel information paradox hypotheses suggest spacetime stores quantum information, preserving black hole data rather than erasing it. Such advancements portray black hole interiors not as mere obscurity but keys to universal secrets. Yet, however alluring the external cosmos, we must ultimately return to our local group, our galaxy, home to a star named the Sun and, in its habitable zone, a beautiful azure planet. At least for now, our sole domicile. This odyssey renders life's fragility and miracle more cherished than ever. As with 2025's latest discoveries, like black holes potentially possessing fuzzy surfaces per quantum models, or Barnardo's radiation stabilizing matter ingestion, the universe brims with enigmas yet, ignite